What's up, everybody? Welcome back to yet another episode of Basic CHEM 101 with Sihlebonan. My name is Sihlebonan, and today we are continuing with Stoichiometry, but we're focusing on limiting and excess reactants. Let's take a look.
Let's go. This is for every child that wants to make it one day. Izimbo class and presence of mind is elsewhere. Swinga usudlani afuna kudledlale. Already alisipani and the timer is nowhere. I know your pain, you don't have to be scared. The dreams are very pure, they are written in focus. Keep that pen and paper, they will take you to that day. In the meantime, stand up, help me.
When different amounts of reactants are added together, one may get entirely consumed, one may be left at the end of the reaction. The one that is entirely consumed during the reaction is called the limiting reactant. The one that is left during the reaction is called the excess reactant. Therefore, the product in the reaction is entirely dependent on the limiting reactant. So what do we mean by this? Let's get to some examples and then maybe we'll understand what do we mean by limiting an excess reactant. Now let's look at what we already know to try and explain what is the limiting reactant and the excess reactant. Remember when we did the last example in the last video, we said 4.23 milligrams of acetic acid and 4.51 milligrams of oxygen will give us 6.21 milligrams of carbon dioxide. Now, carbon dioxide will always depend on the amounts of your reactants. So if we look at this in terms of moles, you'd see that this one. So what we'll be looking for is how many moles of carbon dioxide can be produced from each of these reactants, and then from there we can be able to determine which one is the limiting reactant. So if you look at acetic acid, you'd get your moles, and then to get the moles of carbon dioxide, you will relate acetic acid to carbon dioxide. So for 2 moles of carbon dioxide, it's 1 mole of acetic acid. And then this would give us 0.00041 moles of carbon dioxide if you have this amount of acetic acid. And if you look at oxygen, for 2 moles of carbon dioxide, there's 2 moles of oxygen. Then this gives us 0.00141 mole of carbon dioxide. So if you can look at this, this means carbon dioxide depends on both if you have these amounts. So these are fairly balanced. So this is in an ideal situation where everything is balanced, everything is equal. But for you to see that everything is equal, you have to use moles and then relate it to what you'll be looking for, which is your product. Now imagine if this was not 4.51 and it was actually 5 milligrams. So if oxygen was 5 milligrams, then this would mean for 5 milligrams of oxygen, how many moles of carbon do you get? 2 moles of carbon dioxide is 2 moles of oxygen gas. Then this would give us 0.00015 6 moles of carbon dioxide. Now, in a situation where your reaction is 4.23 milligrams of acetic acid and 5 milligrams of oxygen, oxygen would give you a higher number of moles if you relate it to carbon. And then this would mean oxygen is the excess reactant. What do you mean? Is when you get to 0.00141 moles of oxygen, the whole of acetic acid will be entirely consumed in that instance. As you move to 156, you only have oxygen in your reaction vessel. So in this case, you'd find that oxygen is the excess reactant and your acetic acid would be your limiting reactant when the amounts or the number of moles are not equal when you relate them in that side. Let's try to illustrate this in a different example. All right, they can give you either the mass or they can give you directly the number of moles, or sometimes they can give you concentration, which would be your molarity, but you'll always have to go back to the number of moles. So in this case, they would say you are given 0.15 mole of aluminium and reacts with hydrogen chloride gas, which is 0.35 mole. They would ask how many number of moles or what mass of aluminium chloride can be produced from here. So what we can do is, for us to know how much of aluminium chloride can be produced, we'll have to relate this to our product. If you look at the number of moles, you can easily assume that 0.15 mole is the limiting, but that is not usually the case. You can only know once you relate it to your product. So in this case, you will have moles of aluminium, then you relate them to aluminium chloride. So if this is 2 moles of aluminium chloride is 2 mole of aluminium, then moles of aluminium chloride would be 0.15 mole. And you do the same thing for this one, which is 0.35 mole of HCl. You relate it to aluminium chloride, which is 2 mole of aluminium chloride is 6 moles of HCl. Then what do you get there? 0.12 mole. So looking at this, if you thought this was the limiting reactant, now when you look at this, you'll find out that actually HCl is the limiting reactant because it can only give you 0.12 moles of your product, which is aluminium chloride. And then from there, you can be, so in this case, let's say HCl is the limiting reactant. So if HCl is the limiting reactant, we can use this number of moles to calculate the mass of aluminium chloride that can be produced from mixing these two. So which is moles of aluminium chloride multiplied by the molar mass, 133.34 grams per mole. Then you would get 15.56 grams of aluminium chloride. So in this, when you mix 0.15 mole of aluminium and 0.35 mole of HCl, you can get a maximum of 15.56 grams of aluminium chloride. Now this maximum amount that you can get is called your theoretical yield. Once you are able to identify your limiting reactant, you can use your limiting reactant to calculate the amount of the required product from using those moles of your limiting reactant. The amount that you get from there, which is the maximum amount that you can get in that particular reaction, is called your theoretical yield. Now, usually what happens in reactions is that there are lots of losses that occur, maybe during transfer or during heating. Some things evaporate, and you find out that when you perform your experiment, you don't actually get what you expected. Now that experimental amount that you get will be your actual yield. Now let's clear up some space. So let's say if you perform your experiment, you calculated that you'd get 15.56 grams of aluminium chloride, and what you actually get is 10 grams of aluminium as your actual. Now, as a chemist, you would want to know how much or how accurate were you, and then you'll have to calculate what is called your percentage yield, which is equal to actual yield divided by theoretical yield times 100%. So in our case, for aluminium chloride, it would be actual yield. Let's say we find 10 grams, you divide it by 15.56 grams, you multiply by 100, and you get 64.27%. So that's how well you did based on your theoretical yields and what you got. So you got 64% of what you expected. So that is your theoretical yield and your percentage yield. What you'll have to remember is that you'll be given either a mass or a number of moles. Then you have to calculate your theoretical yield, but you have to start from knowing your limiting and excess reactant. And then once you get your theoretical yield, maybe you'd be given the actual amount of your products, and then you'll have to calculate the percentage yield. And sometimes you'd be given the amount in terms of molarity or concentration, which is C is equal to N over V, number of moles divided by volume. This would be in mole per liter. So from here, you can be able to convert your molarity first to the number of moles, which would be CV. And then once you get your number of moles, you can use everything that we have spoken about to calculate your, first to find out your limiting and excess reactants, and also to calculate the amount of your theoretical yield. And also you can calculate your percentage yield. Once you are able to do that, it means you have understood what we had spoken about throughout the session. Please don't forget to subscribe and share the video. I will see you on the next one. Thank you very much for watching. This has been Basic Chem 101 with Sihle Bonani. My name is Sihle Bonani. I'm gone.